Surface area and porosity are important physical properties that influence the quality, utility, and handling of many materials, which often must be carefully engineered to perform specific functions. Differences in the surface area and porosity of material that otherwise may have the same physical dimensions can greatly influence its performance characteristics. Therefore, it is critically important that these characteristics be accurately determined and controlled. Physical adsorption is a technique used to characterize the surface and pore features of solids, that is, the material's texture. The characteristics quantified by physical adsorption include surface area, total pore volume, and pore volume distribution by pore size. The physical adsorption analytical technique consists of exposing a carefully prepared sample to an inert gas. Sample preparation is often referred to as degassing, which is a process of cleaning a sample using either evacuation or an inert gas purge while heating to remove weakly adsorbed molecules. The analysis is typically performed at the liquefaction temperature of the gas. When a gas molecule randomly encounters the surface of the sample, it is attracted to the surface by the intrinsic surface energy of the sample, and it may become bound, at least momentarily, to the surface. As the pressure is increased, the number of molecules per unit time striking the surface increases, and correspondingly, the quantity adsorbed increases. In other words, the number of molecules adsorbed at any instant in time increases as a function of increasing pressure. As pressure increases, multiple layers of molecules are produced on the free surface and on pore walls. Ultimately, the surface is completely covered and pores are filled. Adsorption of a gas by a solid is the result of the forces of attraction between the individual molecules of gas and the atoms or ions composing the solid. The forces which bring about adsorption include attractive forces and repulsive forces, in addition to the coulombic forces if either the solid or the gas is polar in nature. The energy involved in physical adsorption does not exceed 40 to 50 kilojoules per mole. Thus, the adsorbed molecules can be easily removed or desorbed by decreasing the pressure over the sample or by increasing the temperature. Adsorption starts to build up as the pressure of the gas increases. However, we often refer to the relative pressure rather than the absolute pressure. Relative pressure is simply the ratio of absolute pressure to the saturation pressure, the saturation pressure being the vapor pressure of a pure liquid. During an adsorption analysis, the absolute pressure approaches the saturation pressure, which, for the most commonly used gases such as nitrogen and argon, is close to atmospheric pressure. At this point, adsorption is maximized, and as pressure is systematically reduced, desorption occurs. The quantity of molecules adsorbed or desorbed as a function of the relative pressure is known as the adsorption and desorption isotherms, respectively. The shape of the adsorption isotherm is the fingerprint of the texture of the solid. There are 6 types of adsorption isotherms relating to different textures of solids according to the Brunauer, Deming, and Teller classification. This example shows a type 1 or Langmuir adsorption isotherm as it is normally called. It is characterized by a plateau which is nearly horizontal, intersects the relative pressure axis sharply, and does not exhibit hysteresis in the desorption curve except in a few cases. The plateau on the adsorption isotherm exists because the pores are so narrow that they are filled at low pressure, meaning below 0.01 relative pressure. Once the pores are filled, the remaining adsorption is on the exterior of the porous material. Therefore, this isotherm shape is associated with micropore solids in which pores do not exceed 2 nanometers in diameter. This type of isotherm is exhibited by different materials such as zeolites, activated carbons, charcoals, and metal organic frameworks. These solids exhibit very high surface area, sometimes exceeding 1,000 meters squared per gram. This slide shows isotherms type 2 and type 4. These two isotherms are very similar in shape, with the difference being that type 4 exhibits hysteresis between the adsorption and desorption branches of the isotherm. Hysteresis is commonly observed for porous materials and is observed when the shape of the pores causes the adsorption and desorption portions of the isotherm to have a different path. This difference is what we refer to as hysteresis. This type of isotherm corresponds to mesoporous materials with pore width ranging between 2 and 50 nanometers. The type 2 isotherm does not show any hysteresis, and saturation takes place at much higher relative pressure. These adsorption characteristics correspond to non-porous solids or solids having very large pores called macropores, which are larger than 50 nanometers in diameter. This example shows type 3 and type 5 adsorption isotherms. Like the types 2 and 4 isotherms, these two isotherms are very similar in shape, but are quite different from the previous isotherms since they don't have a plateau indicating a completion of the monolayer. This effect is due to the occurrence of the interaction between two adsorpting molecules being much stronger than the interaction between the molecule and the surface of the solid. Type 3 and type 5 may be observed for water adsorption on carbon, in which case the hydrophobic carbon does not adsorb the water, and any observed absorption may be attributed to condensation of water rather than adsorption. The type 5 isotherm exhibits hysteresis, and capillary condensation takes place at intermediate relative pressure. The type 5 adsorption isotherm corresponds to mesoporous materials, while type 3 corresponds to solids having large pores. This slide illustrates a type 6 adsorption isotherm. This isotherm corresponds to a non-porous adsorbent with a completely uniform surface. The uptake of gas takes place layer by layer, the formation of each layer giving rise to a new step in the isotherm until bulk condensation of the gas occurs. Such an isotherm can be generated by adsorbing krypton at 90 Kelvin on a carbon black graphitized at 2700 degrees C. Adsorption begins with relatively few molecules adsorbed on the surface as pressure begins to increase. At about 0.05 relative pressure, the filling of the first layer on the solid is being established, which is reflected by the first inflection point, A. The linear region of the isotherm, B, is attributed to the multi-layer adsorption on the surface. The Langmuir or BET models may be used to assess the monolayer capacity and then estimate the specific surface area. The Langmuir equation and its linear form are presented here. The standard form describes the Langmuir isotherm, where the quantity adsorbed is a function of pressure. The symbols are as follows. P is the equilibrium pressure. Q sub A is the quantity of gas adsorbed at a specific pressure. Q sub M is the quantity of gas required to produce a monolayer. And B is a Langmuir constant. If the isotherm data conforms to the Langmuir model, a simple graph of pressure divided by quantity adsorbed versus pressure will yield a linear relationship. The slope of the linear region, which equals 1 over Q sub M, allows the numerical value of the monolayer capacity to be determined. Here is an example of nitrogen adsorption on a typical zeolite. Types X and Y zeolites are commonly referred to as phlogisite, and type X is commonly named 13X. They both exhibit the typical type 1 isotherm. Using the Langmuir transform, it is easily observed that the plot of pressure divided by quantity adsorbed versus pressure yields a linear relationship as predicted by the Langmuir equation.